Hello, today I'm going to talk about machine learning and binary decisions and a problem of hyperplane. So I got inspired by Goodigo, and this is a picture I stole from his stream. So you have two data sets, a positive and a negative one, and he said basically that you have a set that you want to consider as positive and a set that you want to consider as negative. So for a binary decision, so yes or no, and you want to have a hyperplane that will separate the plus and the minus. So my first idea for this problem was to calculate the centroid of the plus and the centroid of the minus in order to determine the normal of uh, the the, the sets, but it turned out that he didn't need it because his problem only matters for one element of the positive data set and one element of the negative data set. So let's have the actual sentence. Show that irrespective of the dimensionality of the data space, a dataset consisting of just two data points, one from each class, is sufficient to determine the location of the maximum margin hyperplane. So I forgot to mention is that the margin between the closest plus and the closest minus must be maximum. So I don't know exactly what irrespective of the dimensionality of the data space, so maybe it means for all space Rn for all n, but I don't know, I'm not sure about what if it's a COMC thingy. So I just deal with the hyperplane thingy. So I note C plus and C minus, the two data points from each class in a Rn space. So in a canonical base, so Egg-born, EI, BI, yeah. So I note it as a sum of AI, EI, with EI being the elements of canonical base, and obviously we sum over n, but it's implicit. So we've got AI for C plus and BI for C minus. So my first thing is I want to calculate the vector between B and C, between C plus and C minus. So I just do the difference and I get this result. Now there is not much problem. So what we calculated is the vector from this part to this part. And what we want is that this thingy must be the normal of the hyperplane. So this is how we build it, because it will mean that all the elements of the other part will not be outside of it, since this is the closest element to the hyperplane. So we build an hyperplane so that this vector is the normal of the hyperplane. So in general, the equation of an hyperplane is a sum of dy xy, with xy being the unknowns of the system, and dy being coefficients, are equal to a lambda, with a lambda being real. So now we replace it so that the v is the normal to this hyperplane. So we get a sum of ay minus by, so the components of v, time xy, that is equal to lambda. So now we know that we know this equation. So the set of all hyperplanes being was normal are v is span, so vect in French, vect, so span over lambda of this equation. So now we want the second condition. So we will build a hyperplane ES so that the middle of the line C plus, C minus is in this hyperplane. So we replace xy with the coordinates taken by the middle line. So the middle line is the sum divided by 2. for each component because we are in Euclidean space. So lambda is equal to the sum of a minus y xi, but we replace xi with ai plus bi over 2. We can factorize by 2 in front. Since we have n elements, we have 1 over 2n. And we recognize a minus bi times a plus bi, which factorizes by ai squared minus bi squared. Yes. So once we have this, we have our lambda. So we can write our equation ES being ai minus bi times xy is equal to 1 over 2n sum of ai squared minus bi squared. Now we want to verify that it follows the maximum margin criteria. So we calculate the vector between C plus and the middle, so the middle of C plus, C minus, so it's equal to A minus AI plus BI over 2. So you simplify, you get this. If you calculate the vector between C minus and the middle of the line, it's equal to minus the same result. So they have the same length because it's the middle. But we want to verify that the plane that verify the maximum margin has the same length as the one we calculated earlier. So the first case, we consider epsilon being positive. So we have one hyperplane. We have one hyperplane, and we consider one that is shifted by. So we take the middle. We have one that is normal and that passes through the middle, and we shift it by plus epsilon. So we have our shift in epsilon, and we'll see what happens. So we note L plus epsilon, the margin between the hyperplane ES. Well, not ES because ES is the one we noted earlier, but with another hyperplane that fits the condition, and C plus. So we add epsilon, and we note obviously n minus epsilon, the margin between the new hyperplane with C minus. Why? Because we are in the normal, and if you add plus epsilon, in a sense, you have minus epsilon as the margin on the other side. So we want to maximize both, so we take the minimum and we will maximize it. So the minimum of L plus epsilon, L minus epsilon is L minus epsilon. We want to maximize it, we get the maximum of L minus epsilon is L, because this maximum is reached in L. So this means that the only possibilities for epsilon positive is that it's equal to 0 because it's in the middle. So it's reached in L. Now the second case with epsilon negative, so we do the same hypothesis, except that now L plus epsilon is the maximum because epsilon is negative, and when we maximize it we get L. So that's our conclusion, because if there is a maximum margin condition, then it verifies the one we calculated earlier, and we have proved the unicity, that it exists and that it's unique. So this hyperplane is unique and it's sufficient to draw the maximum. So thank you for watching. I'm just going to conclude on the description of the problem. So irrespective of the dimensionality of the data space, I mean, I think it means for n of Rn, so because we are dealing with Rn vectors, a data set, so the two sets plus and minus that consist of two data points, C plus and C minus, is sufficient to determine the location of the maximum. So the location is a bit weird, but the maximum margin hyperplane is the equation we've set earlier. That's all for this problem. Thank you for watching. I hope you enjoyed it. If you have any questions, feel free to ask them in the comments. And bye.